There are some situations that come up with our discrete distributions that are so common that people name them. So the first one is the geometric distribution. We use the geometric distribution when we have a sequence of independent trials, so each trial doesn't affect the other one. Each trial has either a success or a failure, so there's only two options. Okay? And there's a constant probability of success, P. And here's the main part, is we want to count how many trials we need to get our first success. So X will be our random variable. It will be the number of trials up to and including the first success. So the possible X values, because we want the first success, we have to do it at least one time. So our possible X values are 1, 2, 3, etc. There's no upper limit because we want the first success. Maybe that takes us 3 times, maybe it takes us 1,000,000 times. Now, if we know that something fits this criteria, we can say, oh, it's a geometric distribution. And instead of finding the PMF using logic and our probability rules, and instead of finding the expected value by hand and the variance by hand, we can use these shortcut formulas. So we have the probability that X equals a specific value is this formula. We have the probability that X is less than or equal to some number will be this formula. We have the expected value of X and the variance of X. So we decide to flip a fair coin until we get a head. Let X be the number of times we have to flip the coin to get the first head. We have to flip the coin to get the first head. So what is the PMF? If I wanted to fill it out, the possible X values are 1, 2, 3, 4, 5, etc. And it keeps going. It doesn't stop at 12, it keeps going. The probability just got so small that I didn't want to keep writing them down. So the probability that X will be equal to 1, instead of having to do a tree diagram and find all of this by hand, okay, which can be difficult, I can just use my formula. So we're up here, probably that X is equal to some specific value. It's going to be 1 minus P. Okay. Well, what is P? We're flipping a fair coin, so P is going to be equal to 0.5. So it's going to be 1 minus 0.5 to the power of X minus 1. So X is 1, so 1 minus 1 times P, which is 0.5. What this represents is we need to have one success, okay, and we need to have X minus 1 failures. So this is the probability of failing. 1 minus P is the probability of failing, and we want X minus 1 failures. So this part is X minus 1 failures. That's why it's that formula. Okay, so let's see what this is. This would be 0.5. And the probability that X equals 2 is going to be 1 minus 0.5 to the power of 2 minus 1 times 0.5. This should give me 0.25. And for the probability that X equals 3, that's going to be 1 minus 0.5 to the power of 3 minus 1 times 0.5, which gives me 0.125. And we just keep going, and these probabilities get smaller and smaller and smaller. You can see what the PMF looks like. We start off with a probability of 0.5, so 0.5 probability that we have to flip it 1 time to get our first head, 0.25 probability that we have to flip it 2 times to get our first head, and it just gets smaller and smaller. So let's find a few probabilities. Find the probability that X is less than or equal to 3. Okay, I wrote down the formula here so that we can use it. So the probability that X is less than or equal to 3 is going to be 1 minus 0.5, because P equals 0.5, to the power of 3. So this gives me 0.875. So about 87.5% chance that we only have to flip it up to 3 times to get our first head, which makes sense. If you have a 0.5 probability, you should probably get it fairly soon. What about the probability that we have to flip it more than 7 times? Now this one is deceptively complicated. So you want the probability that X is greater than 7. Our formula only works for S less than or equal to X. So let's see if we can change this. So if my possible values were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. Okay. We want the chance that we have to flip it more than 7 times, which means we didn't actually want to include the 7. So we wanted to include 8, 9, 10, etc. So what is the complement? The complement is actually going to be the 1 through 7. So this is actually going to be 1 minus the probability that x is less than or equal to 7. So I'm going to just look at the complement. Okay. So this is going to be 1 minus, and now everything in brackets, 1 minus 1 minus 0.5 to the power of 7. I realize that's a lot of 1 minuses. If I did that correctly, I should get 0.0078125. So let's find now the expected value of x. I wrote down the formula for us so that we can see it. We'll change colors. So the expected value of x is just going to be 1 over p, so 1 over 0.5, which gives me 2. The variance of x is going to be 1 minus 0.5 over 0.5 squared, which should give me 2. Okay, this is truly just a coincidence. Those are different formulas. It's just the fact that it happened to be 0.5 that this ended up being this way. And standard deviation of x, we're just going to take the square root of the variance. So the square root of 2, which gives me 1.414. Okay. So on average, we will have to flip it about, let's look at our expected value, 2 times. That's the expected value of x. Give or take the standard deviation, which is 1.414, times to get our first head. So let's look at the game of roulette again. In roulette, if you bet on a number, you have a 1 out of 38 chance to win. Let's suppose we want to play until we win and then stop. So x will be the number of times to the first win. Okay. Now let's go back and think about all the conditions. Okay. If you go back up and look at the conditions for a geometric, okay, we have to have a sequence of independent trials. So each game shouldn't affect the next game. Okay, that sounds like a geometric. The next one is each trial has either a success or failure, so you can either win or lose. Then there has to be a constant probability of success, P, so every time we have a 1 out of 38 chance to win. Yep, that sounds good. And we want to count how many trials up to and including our first success. Yep, so because we want to know how many times we're playing until we get our first win. So let's find the probability that we have to play 5 times. In our case, the chance of winning is 1 out of 38. So the probability that we have to play 5 times at x equals 5 is going to be 1 minus 1 out of 38 raised to the power of 5 minus 1 times the probability of winning, which is 1 out of 38. So we have to lose 4 times and win 1 time. Okay, so this is about 0.023. So a fairly small chance that we have to play exactly 5 times before we get our first win. Let's find the probability that we want to play at most 4 times. So that's looking for the probability that x is less than or equal to 4. So we'll do 1 minus, so because it's that less than or equal to probability, we have our different formulas. So it's 1 minus 4 to the, sorry, p. P is 1 out of 38 raised to the power of 4. So if we put this in, we should get about 0.1012. Now, how many times do you think you're going to have to play on average to get our first win? So we want the expected value, which is just 1 over p. So it's just 1 over 38, okay, which gives me 38. So on average, it's going to take about 38 plays to hit our number once. Let's put a give or take on that number by finding the variance first. So variance is going to be 1 minus our p, which is 1 over 38, over our probability p squared, which should give me 1,406. So if I want my standard deviation of x, I just take the square root of that, which gives me 37.5. So what this means is, on average, we'll have to play about 38 times to get our first win, give or take 37.5 times. So that's our geometric distribution. It takes us up to our first win, or our first success. The other one that's very common, much more common actually, is called the binomial distribution. We use the binomial distribution when we want to count the number of successes, x, out of n trials. We've actually done a lot of distributions so far in this class when we were drawing out all those tree diagrams that happen to be a binomial distribution. So we use this when there is a fixed number of trials, n. We know in advance how many times we'll do it. The n trials are all independent, so they don't affect each other. Each success has to be classified. Each trial has only two options, success or failure. And the probability of a success, p, is the same for each trial. So that's one of the reasons they have to be independent. They can't be affecting each other. We can't have conditional probabilities that change based on which turn it is. So the distribution of x, which we'll call the count of successes in the binomial setting, is called the binomial distribution with parameters n and p. We say that x is distributed binomial with the parameters n, comma, p. Okay, then our probability mass function, or the probability that x equals a specific value, is n times x. Sorry, this is n choose x is the binomial coefficient, okay, times the probability of success raised to the x power, times 1 minus p, so that's the probability of failure, raised to the power of n minus x. So n choose x, that's the binomial coefficient. It accounts for the number of ways in which we can choose x successes from n observations. Okay. P to the power of x accounts for the probability of getting x successes, and 1 minus p to the power of n minus x accounts for getting n minus x failures. So I want to go back briefly back to example 131 on page 111. I want to show you how this was actually a binomial distribution. We knew in advance we had 3 questions. We had each time a probability of 0.8 of answering it correctly because each question was independent, and we wanted to see how many successes we got. Okay, and so as you went through, if we wanted a value of like x, we had to figure out how many ways we could get 3 correct. But if you wanted a value of 2, you had to figure out there were 3 different ways that I could get a value of 2. So that's the binomial coefficient. The n choose x, that's how many ways we could get it. And then if you look at it, like to get 2 successes, we had to do probability of success times probability of success times probability of failure. So let's come back now to where we actually are. Okay. So we do how many ways could I get that number of successes times the probability, and I want to repeat that however many times I actually want to get a success, times the probability of failure repeated the number of times you want to get failures. And we have formulas for the expected value of x, which is just n times p, and the variance of x, which is np times 1 minus p. There's not a nice way to find the probability that x is less than or equal to a specific value. We have to actually do that by hand. So we can use R to find our binomial distributions. If we want to do the combination part, n choose x, we type choose n comma x. If you want to find the probability that x equals a specific value, we use what's called d binom for binomial. X comma n comma p. D was for density. Okay. And if we want the probability that x is less than or equal to x, then we do p binom, x comma n comma p. So for our first example, every American football game starts with a coin toss. At one point in 2016, the New England Patriots had won 19 out of 25 coin tosses. Someone thought this was pretty suspicious. Let's see if it was suspicious. So first, let's verify that x, which is the number of successes in 25 coin tosses, has a binomial distribution. So let's go through each of our steps. There is a fixed number of trials n. We know that we're doing it 25 times. The n trials are all independent. They don't affect each other. These are coin tosses. They shouldn't affect each other, so I'd say yes. Each trial is either success or failure, like it's either heads or tails, you win or you lose, yes. The probability of success is the same for each trial. Every time you should have a probability of 0.5. It should stay the same, so yes. So this is a binomial distribution. Now let's find the probability of 19 successes out of 25 tosses. So the probability that x equals a specific value is this formula. So the probability that x equals 19, we want 19 successes, x equals 19 is going to be this binomial coefficient. We're going to do 25 choose 19 times the probability of 0.5 raised to the power of x, which we wanted 19 successes, then the probability of failure, which is 1 minus 0.5, raised to the power of 25 minus 19, because we need that many failures. Okay. Now, let's actually go to R and put it all into R instead of doing it by hand. So in R, we're going to do a D binom because I want a specific probability. Okay. And if you look at our code, okay, it's X, the number of successes, and the total number of trials, comma, P. So we want 19 successes out of 25 trials, and the probability of success is 0.5. So we go to RStudio, pull up a new R script, and we'll do dbinom, 19 successes, 25 trials, 0.5 probability of success, and the chance of that is 0.005277. So 0.0527. Now, why do you think I asked you to find the probability of at least 19 successes? Why would we be interested in at least 19 successes and not just maybe say 19 successes? In statistics, we traditionally are going to always look for something as suspicious as what we got or even more extreme. So in statistics, we look at how suspicious would it be to get what we got or something even more extreme. Okay. So in our case, we got 19 out of 25 successes, but it'd be even more suspicious if we got 20 successes. Sorry, my keyboard's weird. If we got 20 successes or 21 successes or 22 successes, each of those would be even more suspicious. So we look at how suspicious is it to get what we got or something even more extreme. So the probability of getting at least 19 successes on a fair coin flip is only 0.00204. So for a fair coin flip, there is only a 0.2% chance to get 19 or more heads or successes, if you will, in 25 tries. So this does seem very suspicious. Maybe there was something going on. Maybe they were just very lucky, but it does seem very suspicious to me. So let's look at our next example. Let's recall that Charles Wells, the man who broke the bank for the Monte Carlo game, won 23 out of his 30 games of roulette. Now, assuming that he bet on red each time, he should have had an 18 out of 38 chance to win each time. So let's verify that X, which is the number of wins in 30 games, is a binomial distribution. So one condition is that you have to have a fixed number of trials. We know in advance we're doing it 30 times. So yep, the trials are all independent. Each one shouldn't affect the other one. We're playing roulette. Each spin should be independent. Each trial is classified as either success or failure. So you're either going to win or lose. Only two options, yep. And the probability of success is the same each time. So every time he plays, he has the same chance to win. Yep, that looks good. Our probability of winning is 18 out of 38. Okay. So we could say that X is a binomial distribution. Okay. We can write out the whole word binomial. Some people just write BIN. So it's a binomial distribution. And we say it's 25 tries. So we'll say N equals 25, P equals 18 out of 38. That's the distribution. Now let's find the actual probability of winning 23 out of 30 games. So we're looking for the probability that X equals 23. I could plug it into the formula, but I prefer to just put it into R. So in R, we'll do D binom. We want to win 23 times out of 30 total. We have an 18 out of 38 chance to win. So you do the X value you're interested in, the N value, and then the P value when you plug it into R. So let's go put it into R and see what that gives me. Now let's find the probability of at least 19 successes out of 25 trials. So we're looking for the probability that X is at least 19. Okay. Now the problem is, if you go back and look at the way that our p-binom function works. It only gives you the probability that x is less than or equal to a specific value. Okay, the problem is I want it to be greater than or equal to 19. Okay, so this is actually, the probability that x is at least 19 is actually equal to 1 minus the probability. We're going to use the complement rule here. We're going to look for x less than or equal to 18. Now here's the thing, I have to change it because if I want to include 19 in what I want, I can't include it when I take it out of the complement. So I like to make sure I always do it correctly, I like to write down a few of the values. So if we have 17, 18, 19, 20, dot, 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 okay, I want x greater than or equal to 19. The complement, though, is actually that x is less than or equal to 18. That's the complement, okay? And so when I do the complement rule, I have to do 1 minus the probability that x is less than or equal to 18. So it does get a little bit more complicated. So in R, I'm just going to do 1 minus, I'm going to do p-binom. I want the 18 successes, 25 trials, and 0.5 chance of success. So it's going to be 1 minus, let's go figure out what that probability is. So I earn p-binom of 1825.5. I get 0.9926. So 1 minus 0.9926, which gives me 0.0074. So that was the chance of getting at least 19 out of 25 successes. Well, why did we say at least 19 successes? Why didn't we just do exactly 19 successes? Well, the thing is, in statistics, we are always interested in seeing how suspicious is it if we got what we got or something more extreme. So let me pause and write. So I always look at what we got or something more extreme. So then we can say, in this situation, for 25 coin flips, there is only a 0.7% chance of getting 19 of what you want, successes. Okay, or more, something even more extreme. This is very, very suspicious. Maybe it really happened, but maybe those conspiracy theorists had a point. Maybe some cheating was going on. So let's look at another example. Remember Charles Wells, the person who broke the bank in Monte Carlo? He won 23 out of 30 games of roulette. Assuming that he bet on red each time, he should have had an 18 out of 38 chance to win each time. So let's verify that x, which is the number of wins in 30 games, has a binomial distribution. So first we check, is there a fixed number of trials? We knew we were doing 30 games. Okay. The trials are all independent. Each game shouldn't affect the next game. Yeah. Each trial is either success or failure. In our case, it's either win or lose. There's only two options. Yep. And the probability of success is the same every time. Okay. Yep. Every time is going to be 18 out of 38. So if I want to find the actual probability of winning 23 out of 30 games, I look for the probability that x equals 23. Okay. So in R, I'm going to type in d binom. I want to win 23 times out of 30, and the chance of winning was 18 out of 38, and I can just type it in as a fraction, and R will do that for me. So that's right here, d binom 20, 30, 18 out of 38. If we run that, we had that it was 0.000782. So 0.000782. So there's a pretty small chance that he won exactly 23 times. But we might want to say, what's the chance of him winning that or something more extreme? So let's find the probability of him winning at least 23 out of 30 times. Because if 23 is suspicious, 24 would be even more suspicious than 25, etc. So I always look for something more extreme. So now we want the probability that x is at least 23. Okay, and you have to sit down and figure out what is the complement rule here. Make sure you do it correctly. So again, I like to draw it out and say, okay, my choices were like 20, 21, 22, 23, 24, 25, etc. So if I want the probability that x is at least 23, what's the complement? The complement is the probability that x is less than or equal to 22. So you'd have to be very careful with that. So the probability that x is greater than or equal to 23 is going to be 1 minus the probability that x is less than or equal to 23. So we're going to do 1 minus, we're going to do p binom. Sorry, I wrote 23. 1 minus the probability that x is less than or equal to 22. Hopefully you got that. So we want to put in 22. There were 30 total. The chance of winning was 18 out of 38. So it's going to be 1 minus. Let's go figure out what we get here. So p binom, I got 0.9989. So 1 minus 0.9989. So this gives me 1 minus 0.9989. So we had a 0.0011 chance here. So do you think that Wells had some inside help, as some have claimed, and explain this? So I could say something like, if it was fair, there was only a 0.11% chance that he could have won 23 or more out of 30 games. That seems very suspicious. I don't believe he wasn't cheating. Now this is basically, we just did a hypothesis test, which is something that we do later in the semester. This would be what we call our p-value later. We're saying if it was fair, there's only this chance that he could have actually done what happened. Okay, that's suspicious. I don't actually think he wasn't cheating. Now I'm asking you, how many times would you expect him to win out of 30 games, give or take how much? So anytime you see that, I'm asking you to find the expected value and standard deviation. So expected value of x, okay, come back up to your formulas. Expected value of x is n times p, and the variance is np times 1 minus p. So expected value of x is just n times p. So in our case, we're playing 30 times. The chance of winning is 18 out of 38. So this gives me 14.2. And the variance of x equals np times 1 minus p. So we get 30 times 18 out of 38 times 1 minus 18 out of 38, which gives me 7.5. And what does this all mean? This means if he plays 30 times, we expect him to win 14.2 times, give or take about 7.5 times. So we expected him to win about 14 times. He actually won 23 times. Again, that ended up being suspicious. I said 7.5 times. I am so sorry, was not paying enough attention. Okay. The standard deviation of x is equal to the square root of the variance. So the square root of 7.5, which gives me 2.74. Okay. So coming here, if he plays 30 times, we'd expect him to win about 14.2 times, give or take about 2.74 times. Okay, that actually makes more sense. I'm sorry, I apologize for that. Let's do one more problem just for practice. If both parents in a family have brown eyes but carry a copy of the recessive gene for blue eyes, the probability that a child has blue eyes is 0.25. Let x be the number of blue-eyed children in a family with 5 kids. Okay. So first, verify that x has a binomial distribution. So first, we know there are 5 kids. The trials are all independent. We'll assume that each child's eyes doesn't affect the next child's eyes. Every trial is success or failure. So in our case, it's blue or not. Okay. And the probability of success is the same for each child. So every child has the same probability of 0.25 to have blue eyes. So yes. What's the probability that 5 of the children have blue eyes? So we're looking for the probability that x equals 5. So in R, we're going to do d binom. We want 5 children to have blue eyes out of 5 total. And the probability of success is 0.25. Coming to R, let's go put that in. So d binom, 5 successes out of 5 trials, 0.25 chance of success. We get 0.000976. So that was 30976. So that is a very small chance that all 5 children have blue eyes, which is interesting because you think but 25%. That's a pretty high chance of blue eyes, but a very small chance that all 5 ended up with blue eyes. Okay, what's the probability that at least one of the children has blue eyes? So probability that X is at least 1. Well, if you remember, the complement rule that we've been doing over and over for at least 1 says that's equal to 1 minus the probability of none, right? Or the probability that X equals 0. Now, if you don't believe me, go ahead and do my little sheet here where we say 0, 1, 2, 3, 4, 5. Okay, and say we want the probability that X is at least 1. The complement would be that X equals 0. Okay, and you could also do the probability that X is less than or equal to 0 if you wanted to. But in this case, 0 is the only thing that's left. So let me switch back here. This will just be equal to 1 minus, and I'm going to do d binom of 0, because I'm interested in 0. 5 attempts, 0.25 chance of success. And let's go see what that gives me. So d binom 0, 5, 0.25. Oops. You do have to type the parenthesis. So 0.2373. Now I just want to show you what happened if I did p binom, so the probability that X is less than or equal to 0. Well, there are no other options that are less than 0, so you're just going to get the exact same thing. Okay. So 0.2373. 1 minus 0.2373, which gives me 0.7627. So a pretty high chance at least one will have blue eyes. Now, how many blue-eyed children would we expect on average, give or take how much? So expected value of X is just equal to NP. So in our case, that's going to be 5 times 0.25, which is 1.25. We expect 1 1/4 kids to have blue eyes. The variance of X equals NP times 1 minus P. So that's going to be 5 times 0.25 times 1 minus 0.25. So 0.9375. And if we want the standard deviation of X, we have to do the square root of that. So we get 0.9682. So if I want to write my interpretation, I didn't quite save myself enough room. I'm going to write it here. I'll leave you guys a little bit more room. We could say something like, so we expect on average about 1.25 blue-eyed kids, give or take 0.9682. Now, just to remark, there are many more famous discrete distributions such as Poisson, hypergeometric, negative binomial. We're just only going to do these two in this class. Okay. And I wanted to highlight the differences. Geometric counts the trials until the first success, whereas binomial counts the successes in n trials. Otherwise, each trial is a success or failure. That's for both of them. Both of them say the trials have to be independent. Both of them say that the probability of success is the same for each trial. Okay. Binomial says you have to have a fixed number of trials. You know in advance you're doing it n times. For our notation, we can say X is distributed geometric with the parameter P. X is distributed binomial with parameters n and p. We have formulas for the probability that X equals X. For geometric, your values are only 1, 2, or 3 because you have to get your first success, so you have to do it at least one time. Whereas binomial, you could not have any successes, so X could be 0. Okay. And for binomial, it has to stop at n because you're only doing it n times. You know that in advance. Okay. The expected value formulas are different and the variance formulas are quite different.